So I want you to imagine that you are in an elementary classroom as a student, and it's my class, and in my class you have been learning about fractions. You've been learning about foundationally what a fraction is. You've learned how to create equivalent fractions. You've had this flexible thinking about what the whole unit is. You've added fractions, you subtracted fractions, and then one day, unbeknownst to you, you walk into class and you're about to learn about multiplication of fractions. Now, in my learning theory that I like to think about, and it's supported by research, I'm not going to just show them how to do it. I'm going to expect the students to engage in the thinking. But not just foundationless thinking. They have understandings about fractions. They've built visual models. They've been engaged in a thinking classroom where problem solving and thinking is expected. And so by this moment, this would not be a foreign idea to come in and say, hey, students, today, here's a problem for you. Every box of crackers contains 3.5 cups of crackers. Someone eats 2.5 boxes of crackers over several days. How many cups of crackers were eaten altogether? Now, students have the foundational understandings to attack this problem. They might get into this in a minute, but I hope they recognize that this is a multiplication problem. They know what fractions are, and they have ways of thinking to attack this problem. Now, it will not be efficient. They don't have the efficient algorithm for multiplication of fractions at this stage, but over the next several videos, I want you to see how we can leverage student thinking to build the efficient algorithm rather than just have it be told to them and students mimic it void of understanding. All right, so back to the problem. We want students to first recognize that this is a multiplication problem. What does multiplication mean? We've been using the idea back when we were working with integers that multiplication means copies of. So every box of crackers contains some cups of crackers. So here's a box of crackers, here's a box of crackers, here's a box of crackers, however many boxes of crackers that we are thinking about, and every box of crackers has 3 1/4 cups. 3 1/4 cups. All right, so in this case, what we have is we have 2.5 copies of 3 1/4 because this person ate a box of crackers, they ate a box of crackers, and then they ate a half a box of crackers. But nonetheless, the problem turns into, and this is what we want students to first recognize, is that this is a multiplication problem. We're wondering about 2.5 boxes, so 2.5 copies of 3 1/4. Now, that's the first thing I would be looking for in the classroom, is that students can articulate and explain and justify why multiplication is the issue. Now, before I get into, or before you get into thinking about this problem, I want you to think about what multiplication means. Suppose it was just 2 times 3. 2 copies of 3. This is the thinking. There's a copy of 3, and there's a copy of 3. So 2 copies of 3 can be represented like this, and we can clearly see that 2 copies of 3 is 6. Now, with that little introduction, and I might even talk this through with the group of students about, once they've recognized it as a multiplication problem, I might pull the students together and have a little reminder about what multiplication means, and then say, go back to work. You have to figure out now, what would 2.5 copies of 3 1/4 look like? So here's your challenge. Will you take some time to get out a piece of paper and a pencil, or some manipulatives, virtual manipulatives if you like, and will you think about how would a student who doesn't know the algorithm yet, but they do know some stuff, they know about fractions, they know about multiplication, they've done all the fraction work that you've been doing, but they've just not multiplied yet. How might a student start to unpack what 2.5 copies of 3 1/4 looks like? All right, I'm going to ask you to work on this, fully acknowledging, you should be going to this fully acknowledging that it may not be super efficient, but we don't rush to algorithms. We let the algorithms develop as we leverage student thinking. Watch this progression play out. All right, work on the problem for a few minutes, advance to the next slide, and see how I talk my way through it at least, and hopefully it connects to your thinking as well.